A while back, oh great, someone's doing it, so I'm happy about that. Um, this research largely started 3 years ago because, well, frankly, if you look at any of the research on LLMs and generative AI in science, frankly, if you go further back than 2024, even, the research feels very dated. 2023 is when, in my opinion, very relevant empirical insights and research started being produced that I'm going into. My point being that this is a relatively uh, new field that's exploding. When I say relatively, you know, it seems quaint in some ways that the field's exploding in the way that it is over these past years. And at this point now, if I'm trying to find the most up-to-date research on, for example, like prompting, uh, then it's I generally uh, I hesitate to read articles that come from before the current year. And if it's 6 months old, it generally is outdated. With that said, that's not entirely true. It's just to show that this has exploded recently. And my work in LLMs specifically, and towards this idea of evaluating them, actually started because uh, I was interested in, well, I want to get better at prompting. What empirical research has occurred that shows us what makes a good prompt and what hasn't? And that forced me to ask the question, well, what is good? What is performance? And we all kind of have this hip shot idea of it, but as I found out, it was a question that led me down a rabbit hole that gets me here today. So, anyways, uh, there are 6 points in this presentation that I'm going to be going over. I'm going to sort of set the groundwork, like lay out the foundation. We're going to talk some about the theory that grounds what I'm going to recommend, and then a practical evaluation protocol and how to actually use it and institute it with some examples that I've worked up. Okay, so as we're all aware, right, there's a lot of hype behind generative AI. Some of us may have used it and gotten discouraged because it wasn't what we expected or it wasn't that good, didn't meet our expectations, and some of us have used it and see a lot of potential. Regardless of where you are currently on that spectrum, uh, I do believe that there are lots of use cases for LLMs in science and for the use of science. Now, just generally speaking, AI tool use in science is exploding, right? Um, Using a survey in 2024 is like 57% of scientists who responded said they use some sort of AI tool. And then in 2025, that went up to 84%. I mean, this just shows the kind of escalating growth. People are using it and how they use it, you know, I'm not entirely sure. And I don't know how many people reported, what reporting error there was. Regardless, we can see that there's clearly some sort of AI tool use explosion. And the impact on the way it's leading to new papers is very real, right? Um, Roughly like 3 times more papers and then 4.84 more citations, which is a ridiculous uh, number, but that fits exactly the way I understand generative AI to work when it comes to uh, uh, citing and likes to bloat. But that's a different story. And one of the key concerns that we're all probably worried about is AI slop and AI slop science specifically. Uh, One of the unfortunate realities is that these tools are so good at this point that we can, uh, someone can, we were all worried about paper mills, right? But then now we're moving into a spot with person as paper mill, where they can pump out AI slop science that is not in any way validated or rigorous in any capacity. And so um, that dam is breaking now. One of the bigger concerns is that the models are getting good enough where we're moving to a spot with what I would call it's not AI slop science, but AI plausible science, right? What's being generated is is indistinguishable sometimes at first pass from like a decent scientific output. And with that, come questions about where we are as scientists in this process and what that means broadly for us. Uh, I'm sorry, I'm not going to actually address that unless we decide to talk about it during questions or if someone decides to bring it up. But what I am interested in is using AI for specific tasks and how it can help us generate data or or do a part of like the data science process of our science and do so rigorously and scientifically. And a big important part is having rigorous standards in how we evaluate and present those evaluations, right? We're all familiar. Well, if you're at this presentation, you're probably familiar with, R squared, p-values, right? If we run an OLS regression, we're presenting one of those, right? We're presenting goodness of fit statistics. Well, we're all teaching that. We've all been taught that. And so what kind of standard is there for using LLMs? Well, the truth is it's the Wild West, so there's not much. I want to illustrate something about why evaluation is so important and a way to reorient things. So for me, one of the most illustrative points about generative AI is in playing the game 20 questions with it, right? 20 questions, there's a question asker and someone who responds yes or no to the questions. And so in this case, I ask Claude to play 20 questions and it picks a word, right? And I have 20 questions to guess what that word is. And so I started a session in Claude Code and asked Opus 4.7 with maximum effort, I want to play a game of 20 questions. Ready? It said essentially, yes, I've picked my word. Okay. And then I did something which is a slash branch. Basically, it takes the session and it allows you to continue it as is, but then recall it to the exact point where you branched it. So this becomes an A/B experiment if you wanted to, or something akin to a scientific uh, uh, like clinical trial. And then what I did was I asked, like I just played the game straight for a question. Then I said, oh, well, I've got to run. What was the word? And it said it was lighthouse. In the other session, I asked it to write the word down in a document. And then I just looked at that document and the word was kangaroo. So this is a very important point. Unless we're making LLMs like specifically do what we ask them to, they will just do something that is plausible. So, right, by forcing it to write down the word in a document, it essentially created the memory of it. The other game, it is my suspicion that it was just going to say yes or no until it said, yeah, you guessed it. Like it was going to like come up with an answer that fit everything afterwards. So it was like playing a game. They're both plausibly uh, uh, games of 20 questions, but without like verifying, without finding some way to get immediate feedback or to have it track itself. There was no way to verify that it was actually playing the game correctly. So that said, let's actually move more into the meat of the talk. So what are scientists doing with LLMs? Well, they're frankly doing a lot. The ones that will apply most to this session in evaluation are more LLMs for text analysis. So like classification at scale, right? We have this task. Is this tweet toxic? Return true or false with a label. And so the input, we have this tweet, fake news, try again, loser. Well, that's probably toxic. And the output being true, and then it's labeled as a personal attack. Okay, we get that. Other times, we have a lot of unstructured data, and we're trying to structure it. LLMs can be quite good at this, right? So I do some research in budgeting, so there are lots of PDFs out there. So extracting budget line items from uh, uh, like city documents is a very useful use case of LLMs for me. And so you might see something like this: extract the budget line item. So the LLM's also given, these inputs at scale, and it's able to produce, structured outputs in some way. Uh, I've worked with some scholars who've done qualitative coding, right? They have interview transcripts, and then with some very specific instructions, we're able to get like thematic codes with or without code books in some cases. And then of course there's more synthetic data approaches where you're like maybe giving it a pseudo survey, or you're asking it open-ended questions. In this case, this is an open-ended question version. I think these are all illustrative. We have a clear task, right? And then that task leads to an input. That input then gets processed through the LLM, resulting in an output, right? LLMs seem like this mystery, but at the end of the day, there's some sort of prompt input, some sort of magic that happens behind the scenes, and then an output, which is just word. And if you can structure a task that way, you can get an LLM to at least try it. So the current landscape of evaluation. So we have all these inputs and outputs, or these tasks. Uh, it seems crazy to try putting out there that someone hasn't already tried to establish evaluation frameworks or applied them when they're using these. And the truth is that there are various approaches out there, and it's a bit of the Wild West. Everyone sees the shiny gold of publishing with LLMs, but they're willing to be in a lawless world without rules to do that, right? There are definitely trade-offs, but essentially, I want to go over these 5 kind of points. There's the natural language generation metrics, and those exist. You have, if anyone's familiar, you have like Blue, Rogue, BERT scores. But the issue with this in terms of using it for science is they're built for engineering purposes. They want to see that the desired output is being achieved, right? That 20 questions is being played. It doesn't care that if 20 questions is being played right. It just wants to see that 20 questions is being played, that there's satisfaction from the customer, that the system actually functions input to output, not necessarily that the process is actually happening in a way that's scientifically valid and rigorous. Leaderboards. So this is a big one for a lot of people. You'll hear like performing on this leaderboard or this Q&A, or their leaderboards are very deceptive in that public leaderboards are often gamed by companies rather than being what we consider, like scientific evaluation or metrics. These are really marketing tools for a lot of these organizations. By performing well, they get benefits. And so what does that mean? Well, it means that they're going to train the models to the task, or like, whether they're training like the whole model to just do a task, that's not what I'm saying. But they are going to work on making sure that they're optimizing some of the end of it to do these tasks well. That's not scientific. That doesn't help us translate to similar tasks, because these public leaderboards are also using public data. And that public data does pollute the training data. And if that happens, we cannot generalize past that. And so leaderboards become, best case, a starting point to look at models. But even then, I just won't look at them. I find other reasons to start with certain models versus others. And leaderboards are really just model comparisons on certain tasks. They don't do anything about helping you design prompts, helping you evaluate the actual output. It's just right or wrong. Psychometric methods. So, if you've done survey work, you're probably like, yeah, why don't we just treat it like a survey instrument? Which is fair. There are issues with this, though, in that LLMs, right, generative AI, these are technical systems, and my understanding of psychometric surveys is that they're meant to help address the human element in the survey instrument, right, to help correct human biases. Models certainly have biases, but are they human? Here's a question that I've been working on. I don't have any data, so it's just a teaser. Like, if we start treating these like psychological entities, then we should see well-established constructs, right? Like with multi-question questionnaires, like like psychopathy, that sort of thing. We should be able to run those in models and actually see that constructed. Like, we should be able to see the models respond in ways that are consistent across questions. It's a big one that I didn't actually plan on talking about. So I have nothing else to say about it right now. Human alignment. So you might be thinking, one way we can evaluate is by asking humans to do the same thing. And that is very reasonable. And if nothing else, that is a good starting point. but there are issues with that in terms of humans aren't always right. Number one, there's human bias and human noise. And so what we aren't testing if the model's right. We're testing its alignment with a human on the task. And does that evaluate the model? Sometimes. I definitely think it needs to be part of your training data or your evaluation approach, but it is not the end all be all. And I'll give you another example. I was working with a colleague who was doing some work looking at newspaper articles and trying to determine if a company conducted organizational misconduct based on that. And so they hand coded something like 300 of these. And then I ran a few models and I sent the results back to them with the explanations from the model why it chose what it chose. And they actually changed their coding after the fact because they're like, yeah, that makes sense. Like these edge cases, just because you're an expert in it doesn't mean you're necessarily right all the time, especially when you're going through 300. One of the key differences is we can actually trace back the plausible explanation that the LLM's generating why and audit that. So, okay. And then more to the point, it's like, well, if there is ground truth for a model, like there is a right or wrong with something, like why don't we just use accuracy, the exact match? Well, we should. We should absolutely do it. The problem is that's the only thing most of the literature actually looks at. And the more subjective you get, the harder it becomes to actually do anything. And as anyone who's worked on survey methods knows, there's also quite a bit of other signals that you can actually get from response data, particularly like test retest. I mean, reliability is what we call it. And these models are noisy. They're noisy even when we think they are not. Like you might have heard of temperature, which is a hyperparameter that you can set these models on that, if you set it to 0, the idea is that it's supposed to um, reproduce like its output. And there are even some models where you can set seeds now to potentially reproduce output. So this is where being part of the team and the Institute for Interdisciplinary Data Science pays off, because we have an on-prem inference server and a very good sysadmin/data scientist who's a very curious individual. Like curious as in scientifically curious. As a person, they're great. They're not. But they set temperature to 0, and they ran models even setting seed on some where you could set seed, finding out that they still got non-deterministic results because of the way GPUs function, right? It's like if other things were on the GPU, like a different path actually is taken by the GPU, which means that the nodes present something else. All that to say that these models are non-deterministic, even when we try making them deterministic. So trying to continually replicate is not just a function of setting model parameters, um, uh, and we have to account for the fact that there is some pseudo randomness to these things. Okay. So, I mean, the big point I want to get at is that there are little bits of answers in each of those approaches, but none of them solve the actual root issue that I was searching for, 2 or 3 years ago, which was like, how do I evaluate like what prompts perform empirically better than others? Because it's a question of performance. And there was the question of, well, do I treat these uh, like a computer program? And there's some wisdom in that, but the truth is that what they're representing is something of a human phenomenon in language, right? So that's not entirely the answer. So do I then treat them like people? And no, because they're not. They're also part system. They're part computer. And for a while, I kind of scratched my head about what to do. And my current proposition, which I'm fine anyone pushing back on, but my current proposition is that I treat them like measurement instruments, like a thermometer trying to tell the temperature, right? It is a series of um, like the computational system serves as a way of trying to gauge some sort of phenomenon that we are querying the model about. So the input is what we're hoping to get out of it, and the output is, I mean, if you thought about it like a Geiger counter, right? The reading on the Geiger counter is not the radiation. It is a representation of the radiation. So it is a representation of whatever we're trying to get. And when I think about it like that, it's not perfect, but it does open up different ways to actually evaluate the performance of these things and do so rigorously. So to ground this in some actual theory, we can start with the idea of classical measurement theory, right? And most of us are probably pretty familiar with that. We have some sort of observed measure, we have some sort of true value, and then we have measurement error. That measurement error is bias plus, variance. Um, Bias being equivalent to uh, accuracy, like validity, like how correct is this? And if it's not, is it systematically shifted? And then error being, randomness that comes from noise. And so this actually frames, two important points about these outputs. Like if I'm asking it a true or false, is it responding true? And if I ask it the same thing 5 times, how often is it going to false? Right? We get both the what bias might be in there, uh, and then the noise that comes from asking these non-deterministic machines repeatedly. But uh, that's not the entirety of it, right? Because this isn't just uh, uh, a bias, an error point. And I'll tell you the way uh, I started wrestling with this. That same organizational misconduct study, I ran 3 different models to compare results. And the best performing model was one that on the surface should not have been the best performing one. It was like I ran 2 of the same models, but one with smaller parameters than the other. So it was like 20 billion parameters versus like 60 billion. And the 20 billion performed better. It was more accurate and it didn't vary as much. I was like, why in the world? I'm like, well, if it performs better, it performs better. Maybe the training data did something. Maybe there's something in definitions. I wasn't sure. And then I started looking at the explanations that that the model produced to go along with its responses. And it was basically just restating the question. Whereas the bigger model actually had reasons uh, that seemed plausible to me. It wasn't just, well, this is toxic because that's what toxicity is. Like, that's okay, good job. You just restated the question, but that doesn't actually tell me much about the way things are working. So, why that's important, it doesn't change the fact that it was more accurate. It does change how much I'm willing to believe uh, that model performs as well as I scale it without um, without human coded responses to actually verify, right? These models perform so well at scale. Being able to code 25,000 of those organizational misconduct responses is enormous. What I need to understand is that based on my small sample of human coded elements, how trustworthy is that? How much can I extrapolate the accuracy rate in the small sample to that larger sample? Like what kind of error bands are there? And so there are, um, I when I think about this, not only in terms of the actual response and how variable the response is, but the explanation that it provides, using that as a way to evaluate my trustworthiness of the system as it scales. There's a window there to actually do some scientific and very rigorous evaluation that can be informative. And so I was looking for theoretical framings, and as a social scientist, I was very unaware of metrology until I started doing this. So metrology is the scientific study of measurement, which seems very relevant for this kind of thing. And this is in fact uh, the field of study that basically forms the foundation for NIST, uh, the National Institute for Scientific Standards and Technology. And uh, there are lots of principles in it that don't necessarily translate very well or easily to social science. But when looking at that, there are actually a lot of different ways to think about LLMs and systems and evaluation that can help reframe it's either a program or we treat it like a person, right? But it's a measurement tool producing some sort of output or reading, and we want to assess how not how much error necessarily is in the output, but how certain or uncertain are we uh, of its output. That allows us to be able to scale beyond uh, what we can put our eyes on, what we can actually hand code. And so this is where metrology really uh, helps with everything. And to be clear, it's not meteorology, which is what I first thought it was. I'm like, oh man, I didn't realize the study of weather was so uh, uh, built into uh, measurement studies, and then I realized they're two different words. That's just pulling back the curtain. Um, uh, Metrology, one of the important framings is that they don't necessarily look at output error. They look at output uncertainty, right? And they try to evaluate how much they trust the measurement system, right? They have their ground truth of like a measurement, and then they calibrate that across instruments and have a chain of like, we believe this is an inch because like that was calibrated from this instrument, which was calibrated from this, which was calibrated from the source, right? That's essentially it. They have like traceability chains and various metrics, and they actually calculate the uncertainty and the potential output. And so from here on in this presentation, I'm going to use the terms accuracy, precision, and uncertainty, which take on a very specific meaning for this that is also in a lot of ways correlated with our understanding in social sciences of validity being close to accuracy. Um, uh, Reliability is stated as precision, and then uncertainty, which is different than error, but um, in a lot of ways serving a similar purpose for us for what we're doing in terms of, oh, this is telling us how much we should trust or not trust this data. So, okay, metrology. So the framing, we're moving to using these things like measurement instruments. What does that tell us? How can that help us present things? Well, uh, now I'm moving into more of a practical part of this presentation. And when I think about evaluation, I think about it sort of in two blocks. One is the what gets evaluated, which is the protocol that I'm employing. And then the other is how it gets evaluated. And the how it gets evaluated is what criteria or concepts am I trying to measure? What metrics am I measuring? And what's necessary to be present or not. My hope is that long-term social sciences can develop a very strong foundation for what we expect in terms of evaluation standards. Like if you do an OLS regression, you're pretty much expected to produce p-values, r-squareds, right? And the efficacy of p-values is not on the table here for a discussion, but still you're expected to. Uh, and that's very valuable. Like one of the benefits to the metrology framing of things is that it establishes the credibility of a foot, and we all kind of know what a foot is, or a kilometer. Uh, there's an understanding that comes from general acceptance of an evaluation standard or a measurement of that. So okay, we're going to start with the Tamper framework. So just full disclosure, this is a framework that I developed, and you can follow the link uh, uh, in this slide if you wanted to read more about it. But the Tamper framework is I believe a good starting point for understanding what to evaluate in what to evaluate with LLMs. So the Tamper framework stands for task, model, prompt, evaluation, reporting, right? These are decision points that we all scientists need to come into with LLMs if we're approaching them. This is, of course, putting to the side ethical um, and justice sort of perspectives. But just as a scientist looking at rigorous, uh, credible, trustworthy science, what do we need to do? Well, so evaluation, I believe, starts with understanding what you're actually asking the model to do, right? That's the task. And that seems easy until you try articulating sometimes what you're trying to get a model to do. And I think that I have found that I have more success with these things the more discrete I can make the task. If I can make its input-output binary, true or false, yes or no, I can generally create instructions that lead to results that I believe are credible and scalable. And so if you're curious, like what kind of tasks I might be talking about, what kind of tasks scientists might employ, well, I just go back to this. What are scientists doing, right? Classification at scale, extraction from records. Like these are all specific tasks with discrete outputs. Uh, and so, when we're evaluating these models, we're evaluating some task. And to be more concrete, what we're actually evaluating, regardless, is the output. The black box that is the model. There are some models that make their weights open and you can actually trace what's going on, but that's not something that can be used to compare models very easily or compare outputs. So at the end of the day, I focus on evaluating the actual output of the model as a way of understanding the model and to build evaluation frameworks from there. That gets us to the actual model. Which LLM, how is it configured? And there are lots of decision points with models, but I'll say this. I would not get too bent out of shape trying to optimize the parameters. So like temperature is something we talked about. Top P or top K is another similar hyperparameter. There were studies, and again, this was I think this study was published 2 years ago. So yeah, how credible is it at this point, or how much does it apply? I don't know, but we don't really have standards set or expectations set for what temperature we choose, or at least we haven't actually set that in empirical evaluation. The early work on looking at uh, basically the variability of models based on temperature settings basically showed that it didn't, like a temperature 0 didn't actually produce at least more accurate responses, and actually led to less accurate responses in some cases. And so if anyone's saying like, well, why isn't temperature at 0? That's just an assumption the field's kind of going on. Like there isn't a standard that I've seen. There might be some work that's being published. I'm unfamiliar with it, but open to entertaining it, certainly. One of the other points I want to make about models that has nothing to do with evaluation, actually it does have a little bit to do, but a practical consideration is that a big choice for researchers is what model to choose. And people will often go with state-of-the-art proprietary models because they can see what models do. And I certainly like, Opus 4.7 and 4.6 are great. But for doing scientific repeatable tasks, I barely trust them. I, in fact, avoid them like the plague. I don't know what their system prompt is, like because whatever I'm sending, like right, that input process output, the layer between input and process can be altered by these companies, and I believe has been sometimes like you might submit a prompt and then it would go through a prompt optimization step, and what that looks like, not entirely sure. But the point being that from a scientist perspective, we're trying to reproduce and we're trying to evaluate things as we see them. There isn't reproducibility when steps are hidden, when we can't get access and we can't report on those things. And then there's also the inability to replicate because changes happen to these models, at least proprietary models, behind the scenes all the time. Claude issued a post-mortem like 2 days ago, I think. May have been Friday. I don't know. Weeks or days or weeks now, weeks or days. It just, time doesn't matter. But they basically said they did a test and it messed with the tokens people were doing. And there were lots of people in the developer community pretty irritated at them. And frankly, like, it didn't matter to me because I wasn't doing anything scientific with it. But if I was, it would undermine my ability to replicate. Now, I'm not saying don't ever use state-of-the-art models, but it does require extra reporting. And it does mean that we're not able to actually evaluate the information that's there. There are limits. Okay, so that's off my high horse. What would I use instead? Well, here at the University of Idaho, we're lucky enough to have on-premises servers with local or open source models. So I often will run those because everything's fully replicatable. And I'm not sending data to those companies. Okay, so we can evaluate models to try determining which ones which one we want to select and why. There's also prompts. So what prompt is appropriate for this? And I'll just say one bit that's a bit ancillary to the evaluation. Well, again, sort of, but also not really. When it comes to developing prompts for like a paper, people might be worried about optimizing every word, and then it becomes exhausting and overwhelming. And frankly, I just would not worry about that level of prompt engineering. What I think people, or at least the arguments I've seen that I believe are appropriate and understand the trade-off between optimizing every word and a scientist has a life kind of thing, and also what's credible evidence in that case, is looking at prompts in terms of components, right? So we have some sort of task specification, some sort of classification scale and how that's presented, the context and the instructions, right? Like 4 components. So are there specific instructions for making each of those? Are you leaving parts out? Are you leaving parts in? Like these are the things that we can mostly justify in terms of um, like a design paragraph. But then if you're trying to choose between or justify a certain kind of prompt that goes either against that or maybe uses, for example, an explanation versus not using an explanation. This is what this kind of approach can do, right? Same model, same parameters, different prompts. Which one performs better and what does performance mean? So, okay. So that gets us to evaluation and reporting, right? The task model and prompt are what we're evaluating. And evaluation and reporting standards are, of course, the actions taken on some of those decisions. I'm not going to get into reporting protocols. The field and frankly, science just as a whole is getting much better about trying to create reporting protocols. I frankly feel that the reporting protocols I see, they tend to drift into requiring things that I think are very subjective. Like what path did you take to minimize, insert, what pet cat issue for the research? I'm like, okay, well, I get why that's an important discussion point in the discussion. I don't think that's necessarily part of the required reporting standards, or in terms of creating a generalized reporting framework, right? So anyways, there are plenty of good approaches, and you can look at the Tamper paper if you really want to know what I believe is important to have in there. But I'm not going to spend a ton of time on that. So my protocol, right? I look at the task, I look at models, I look at prompts. I try to separate these out when I'm evaluating. Uh, um, I have an approach that starts with asking what I call a dual response from these models. One part is the direct response, the actual label or the thing that answers the question for the task. And then the second part is the explanation. Why did you choose this? Right? And I believe the dual response is key to doing everything that I've talked about up to this point. So number one, adding an explanation has been shown to improve the actual accuracy of these models, which is really quite nice. It's just one side benefit that I believe is important. My own sort of side research that doesn't see the light of day, but like I've run thousands of models and different calls. Like explanations tend to also reduce, or they increase the precision. They reduce the variability of the outputs, which is quite nice. Also, beyond that, what it does in terms of serving science is it creates an auditable trail. Why did it produce this? Now, there's a discussion that's quite open in the generative AI community of like when you ask for an explanation, is that faithful to why the model chose it? Or is it just a plausible question? We're going back to the 20 questions example right at the beginning, right? Is it creating an explanation to match its output? Or did it reason this explanation and create the output? And I believe reasoning models make this question a bit clearer because you can actually like review the reasoning tokens and then match it to the explanation to make sure that that actually tracks. But it's a fair point. For me, I believe that faithfulness to the model is something that I haven't seen a very good evaluation approach yet. It's more just vibes. Like, yeah, I believe the model. Yeah, I don't. Okay, that's fine. It's not scientific, but what, like that's about as good as it gets. And plausibility, if the output is plausible, if it passes the smell test and passes reasoning tests, I don't see why that's a bad thing in this case. That might, in fact, be showing us that the system, the instrument, is working. Um, so, anyways, the explanation gives us a chance to actually physically put eyes and audit how the model's doing. It also serves to help us evaluate the system in more scalable evaluation ways. So, right, the direct response, it allows us to build, if we want to think about it, like the error metrics from classical measurement theory. We can see how accurate the model is based on the direct response. We can see how precise it is based on the variability of its response on repeated calls. But then the explanation is how we see how well the system's working, how much we trust it to actually be able to do more scalable work. So beyond that, the other sort of linchpin of my protocol is this sample benchmark population approach, which is if we actually could put eyes on everything and create human responses to actually check accuracy of like a full corpus of documents or some enormous task, then we wouldn't need LLMs to do it, right? We just do it by hand. So we have to find some way to get the benefits of human curated responses with also scalable approaches. So the idea is fairly simple. We take a small curated sample from the full population. We have a curated data set on that, one that humans respond to, and we have the LLM responses. And we can create accuracy benchmarks, um, precision benchmarks, and then sort of system evaluation standards. And then we have the LLM run on the full sample, and we can use the benchmark set from the sample to the population, basically. Like the things that aren't accuracy, we can actually relate to on the full population, and we can see, well, is this out of whack? Is it uh, like, do we expect this accuracy to persist given our understanding of uh, of the rest of the system's functioning at scale? And so recently there was I say recently, 2023. Recently, I discovered an article in Science that could help me actually put this plan into action. It's called prediction powered inference. And so uh, I ran just a version of this on some sentiment analysis data I had run. So the sentiment analysis had 2,210 total observations and PPI. We took 200 of those, and natively the point estimate generated from like all the um, sentiments generated, like if I just convert those to numbers, was 2.16, whereas the PPI version was actually 2.055. The true population mean, like when it's scaled up to the 2,210, was 2.053. That was a remarkable find. I did not expect. The other remarkable part of this was that if you look at the confidence intervals in the guarantee part, or the guarantee step, I'll highlight them. The top confidence interval, or the top of the confidence interval, is 2.156. And if you go back to the native point estimate, 2.160, it actually just barely falls outside of the actual confidence interval if you don't adjust for it, right? Just doing a naive sample doesn't actually help you set a benchmark or confidence intervals that you can scale out to a larger corpus. So if you're interested in trying some of that, I think that there are methods being developed that fit well within our understanding and uses in social science. Okay.
Hey, Michael,
Yes.
can I?
Yes, please.
So on that last one,
Mhm.
I might have kind of missed kind of the key idea there. Are you saying that people's assessment? Um, yeah,
So
actually, yeah.
here,
Sorry.
no, no, no.
Mhm.
I'm happy about this. What I assume is clear is often not. So, especially when I'm trying to talk about it, which you know, of course, working
We
for.
all do.
Yeah.
Yeah.
Okay. So here's the idea, right? We have a corpus of like basically Twitter data that has been analyzed using sentiment analysis. Now, this particular corpus has human annotations for the entirety, and it also has LLM annotations for the
Mhm.
entirety. So I actually know what the truth is in it.
The
The
human alignment.
Yeah,
Yeah.
yeah, the human alignment versus LLMs. And in this case, um, what we're trying to do is this sample benchmark population approach. Like, does that actually have some sort of merit? Is there a way to practically do it? And so I just took out 200 um, of those and treated those uh, as human coded and LLM coded. Right, that's our calibration set.
Mhm.
And then the remaining, I pretended didn't have any human coding. The human coding beyond that was just to assess how well the actual um, method
Like a
did.
validation set,
Yeah, exactly. I mean, you
right?
can think about it like that,
Okay.
certainly.
Okay.
So, um, with that, if we just looked at the actual accuracy of just the naive set and tried to extrapolate that to the entirety of the full working data set, it would suggest that 2.160 was like the mean, the population of it. Um, of this, not
Oh,
necessarily
that's
the
the
accuracy of
sentiment
it.
score.
Yeah, yeah, yeah.
Okay.
And
Okay.
uh, and so the PPI adjusted method, like it takes some other like machine learning considerations
Mhm.
into play.
Mhm.
It actually suggested a mean of 2.055, whereas the
Okay.
actual mean of the human coded was 2.053. And
Gotcha.
hopefully I didn't get,
That's
yeah, I got
really
those
close.
right.
Yeah. Okay. So
Exactly.
that's
So
processing.
it's incredibly close. And then like you can use the PPI method to actually generate confidence intervals, which then can be used to generate p-values and whatnot. And so
Okay.
the
Mhm.
confidence intervals then for like what that mean would be um, were such that using the PPI method, right? And I'm going to highlight that on my screen. I don't know if you can see the actual highlight that
Mhm. Yeah.
I'm using. Like the top end, the 2.156 is actually
Mhm.
lower than what the naive 200 suggested.
Mhm.
I didn't I didn't predict it that way. It just happened that way. And I think that it's an interesting use case now. How this method um, translates to actually developing like an accuracy metric. It's a bit
Mhm.
um, wild west frontier. There's a clear way to do it. I just haven't spent the time to take those steps yet. But I wanted to show this idea in practice. Okay, does that make more sense?
Yeah. Thank you.
No problem.
Michael, could I ask a question also?
Go ahead.
Uh, I'm just interested. What's your perspective on the kind of state of the field in social sciences? I mean, this is a brilliant approach of systematic reproducibility or approaching that. Um, I see people use this tool is super easy to use. People are using it all over the place. Like, do you see any alarm in our professional societies and across the fields where people are like, "Wait a minute, this is a five alarm fire." What's your sense?
Yeah, I mean, uh, it's yes. Yes is the answer. The journal editors I've talked about, which I'm going to just assure you that anyone in here has talked with more journal editors than I do. So don't take this as like I'm like in the field, like really. No, but they have all expressed this idea of like the paper mill as individual or person as paper mill being a huge issue, and they've also expressed the commensurate problem with the need for actual human reviewers to meet the need of the moment. But there's a problem, right? We have the scalable input without the scalable review process. Uh, and by nature, we're trying to get humans to review in order to tell if these are AI. So there's panic there where I might be more liberal in my use of AI than other people. This is where it shows because it's like what I care most about is good science. And if AI is producing knowledge that is usable, and uh, I'm kind of okay with it. Now, presenting that as your own work is a different ethical issue that I'm not uh, uh, here to say, but I will use AI quite a bit to write, verify citations, find citations. It doesn't mean that I'm using it to actually think for me, but it is taking a lot of the burden off of what I'm doing. And here's the thing: not everyone's going to be the same in the way they approach that either. In fact, I would say Eric and I are probably on a bit different side of the spectrum on this. Which, look, Eric's brilliant, so I don't think that he's necessarily wrong, but it's something that we are as a field wrestling with. I don't think people realize just how much the new models can do and what that actually means for science as deliverables. Okay, this is a side tangent, but we're about to transition to something else, so I can talk about this here, I think. Um, uh, the, the scientific paper is not research. It's not actually knowledge. It's been a very, very useful tool for disseminating it and for doing a lot of things that are important for the enterprise of science, right? Like we catalog our science in a paper. It gets reviewed as a paper, and then committees look over that for tenure, right? It serves so many different functions at once. So when we have person as paper mill and an eroding of the credibility of our contribution within the scientific process because we don't know where AI begins and ends and where we do in that, or what's credible and what's not credible, it does cause a lot of questions. Now, what I've been doing on my side is thinking like, okay, if AI is making papers potentially irrelevant in the future in terms of like this is the way we're contributing because AI is producing knowledge that's as good or better than what I could do. It's, well, why don't I think bigger? And so I've been toying with the idea of like, I have this question. Let's see what the state of the field is on this question in terms of its scientific life cycle. So rather than focusing on one causal question, I'm focusing on the entirety of evidence and what is missing. So yeah, AI is going to produce some good papers. Why don't I get to produce the missing evidence pieces to really understand this phenomenon, right? If it can produce 30 papers that are all credible, good knowledge, why don't I have it producing 30 good papers in evidence of trying to understand a theory or something else? I mean, what science can be quite a bit bigger, and what we can do and develop with these things is quite enormous. I'm not ready to share much beyond this, but there's like using Claude Code um, and a state-of-the-art model. Like we can have personal information systems that we customize and design for ourselves as scientists that compound on everything we do. Like, oh, I'm doing research on this. Oh, so it goes and collects the articles, and then it summarizes those, puts that into a different knowledge base, so that when you're working on something else, like it can pull that. It's like a giant working brain, right? So I'm a bit optimistic in terms of what it can potentially do. It doesn't mean we're not going to have awkward growing pains like that time in the 8th grade I grew 6 inches and then fully expected to continue growing when I was in 9th grade, and I did not. I stayed that same height. So okay, that's the. Does that at least kind of address your question?
Yeah,
Okay,
that's good. Thanks.
no problem. So moving into criteria, this is, I think, one of the more tangible parts of the actual framework. It's okay, we know what we're doing, and essentially kind of the beginning of the actual protocol. We use a direct answer and an explanation. We have a sample benchmark so that we can align this with humans. But here are the criteria that I essentially see across different tasks, right? We like compliance, accuracy, and precision. I consider the baseline. These are things that every paper should be providing that use LLMs, period. There is not a lot of reverse engineering. They are fairly adaptable. The only one that has some issues adapting is accuracy. So if you're, for example, trying to understand like a chatbot that you built and evaluate its responses, like is there a right response? I think that maybe you can look, did it stay on task, and then like have a pseudo accuracy measure. But that's a bit of a bigger discussion. Beyond that, there are the system level questions. And one of the problems with the broad literature is that depending on what the task is, there are different kinds of quality criteria. If you're asking to review summaries, then there are, like you'll see like relevancy and fluency is big important variables. And then also faithfulness. which is different than the faithfulness I was talking about earlier, which also makes criteria confusing when you're researching it. But that's like you asked the LLM a question, is it using the information you present in your prompt, right? Is it faithful? That's showing that the system's functioning as it should be. And so the quality metrics I've just kind of summarized in these top lines, like linguistic, do we see it operating linguistically as we'd expect? Is it logically operating like what we'd expect? Is it using information appropriately? Is the information fidelity there? And then the informativeness or depth of the response. So as I mentioned, like the criteria kind of get muddled because we have different tasks being evaluated with different quality criteria. This is where the explanation part becomes very appealing to me, in that whatever your task is, if you ask for an explanation, you're now evaluating the explanation, which then creates a shared approach to building up the evaluation over time. Like, yeah, like we can evaluate the quality metrics of evaluation across extraction tasks, across classification, across qualitative coding, like basically the same. So that's one of the bigger appeals about it to me. So with that, I'll get more into detail about each of these in a second. I want to make sure, okay, fine on time. Just so that it's said, right, their accuracy and precision help us understand like the signal and the data. They help us understand, like, okay, is the output like correct as we deem it, and then is it bouncing around a bunch? But then the compliance and quality metrics help us understand the functioning of the instrument. Do I trust this Geiger counter? Like got a clock in my living room that's broken at like 317, and as long as I look at it at 317, it looks accurate. That is not always, that's clearly not the case. Like if I was actually evaluating, like, okay, is it moving every minute? Like I could evaluate the functioning of that system. And so, anyways, moving on. So we'll start with compliance. So these metrics are calculated using a case study from data that Eric has kindly provided on a paper that I want Eric to be on, that he refuses to. For reasons of, I believe quoting him, he doesn't like me as a person. Anyways, that's a joke.
That's a direct quote.
Yeah, direct quote. Okay, well, maybe not a joke. And to be clear, not a good joke at that. But in compliance, we're just trying to see that the model is actually producing what we told it to. And so that involves, is it producing the fields that we asked it to? And is it producing the data types we asked it to? So if the field is producing the wrong data type, like if we ask it for a true or false Boolean and it produces a yes, I would say that's not compliant, even if it's accurate. If we ask it for Boolean true or false and it produces true as a string type variable, non-compliant, because it's not actually producing the type of variable we want. And this can be done with most models in JSON. That's the way they'd actually produce their data and output. And so really compliance is I break down into percent correct data type and percent missing fields, right? Like I'm sorry, well, the inverse of the missing fields. So if it does produce both data types I'm looking for, but one of the fields is empty, it's non-compliant. And as you'll see, in this particular case study, we use 4 models. Command A, which is a Canadian company that does cohere. GPT-OSS, which is the 122 billion parameter model, open source model that OpenAI produced. Phi4, which is an open source Gemini model, and then Quinn 3, which now has newer versions. And then I use 2 different prompts, an established prompt and a revised prompt. And outside of Command A on some established prompts, there was a nearly 100% compliance. There was a field, they were all correct data types, and there were very few missing. The Command A compliance was actually a missing field issue on a few outputs. This is because I use something called structured output. If you're actually working on any very discrete task, I would highly encourage you to look into structured outputs, because it essentially narrows the grammar that models can produce to a very discrete set. There's some interesting, fun things to potentially do with structured output too. So as an example, we had an intern who was like, I wonder if the model reads the structured output and producing its response or not. So it gave a model a blank prompt, but the structured output, which again, the structured output is not fed into the prompt, not at all. It just forces the output in a certain way. The field name for the structured output was a question about Star Wars. So it's like in Star Wars, who is Luke's father? And then the model produced Darth Vader. It clearly read the field name when it was pushing things out. Or another way of saying that is that it was forced to say the question, and so it responded in kind. Anyways, that's as much as I'll go into with structured output. So compliance tells us how functioning the system is. Because of these results, I was like, well, the established prompt that's used often in the field seems to produce some non-compliant results in command A. So I don't necessarily trust it. That gets us to accuracy. How close is the direct output or the direct response to some sort of either objective ground truth or expert judgment? And so with this data, which was a stance detection, if you're curious, you can look at the prompts in the appendix. You're certainly welcome to. Um, uh, we had a human-coded set of data to compare this to. So this was actually a human alignment. And in this case, it's an exact match metric, but there are a number of different ways you can approach actually trying to measure accuracy. And of these, it looks very much like Command A using the revised prompt is going to give us the highest accuracy, whereas Quinn 3 does a pretty good job, and then GPT OSS does a very similar job across both prompts. Now, that's a point estimate, and a point estimate, right, that's very close can also be statistically indistinguishable from another. So what do we do? Well, there are a number of different statistical tests for us to take these accuracy measures that are produced and determine with some bit of evidence and testing whether or not they are different from statistical noise, or if they are statistically like distinguishable or different. And the one I use for accuracy is the McNair test, because it's a paired test where I take a question from, for example, this Command A and its response and accuracy with an established prompt versus a revised prompt. And then I boil that down to a dichotomous variable. Was it correct? Was it not? Right, 1, 0. And then I run the pairwise McNair test, and it tells me if the accuracy is in or outside of the bounds. And this allows me to make a claim if I, like in my research, I'm going to use this because it's the most accurate prompt and it's different than these other models. Or in some cases, I'm going to use GPT OSS and the established prompt because it's statistically indistinguishable from the revised prompt. So it can be used as evidence when we're making our design decisions. Precision. And again, what we might know is variability or reliability. We're looking at output consistency. So I have a grad student, this is unpublished at this point, but they looked at consistency very deeply and basically found there were diminishing returns on what we found after 5 iterations. So I take the same model, same prompt, and ask it the same thing 5 times. And I look at the output, right? And this is both the direct output and the explanation. The results you're looking at are just from the direct output. And so we can then apply our survey methods on like test retest or iterator reliability to these tests. And we can get, for example, Krippendorf's alpha and agreement rate. And if you look at these, what we might see from the evidence is when it comes to Command A, our revised prompt is the most reliable according to Krippendorf's alpha. And that is also true when we look at the agreement rate. And of note, the GPT OSS model, really the variability doesn't matter between prompts, but is also pretty high. Now, there are reasons for that. I've used GPT OSS model enough to know that there's very little prompting that will make it change its mind. It's the annoying, stubborn roommate, if you want to think about it like that. Okay. So I've talked about explanations. How might I actually do that? I want to take a very quick moment to talk about how we can do that sort of at scale. Because we can always put our eyes on it, read it, and assess it. But there are really two methods. One is semantic similarity, and the other is LLM as a judge, where we use LLMs to actually review the explanation and create a qualitative judgment on that. So semantic similarity, if you are unfamiliar with this, I'm going to try going real quick, but the idea goes like this. You can take a word, a sentence, even a paragraph, and you can send that through an embedding process. That embedding process takes that natural language and then creates a multi-dimensional representation with numbers. That comes from various training that is kind of beyond the scope of this. But the idea is we're trying to break down into different dimensions how close the meaning of these things are, not the lexical or like direct word overlap, but the actual meaning. So, the example I give here is I love my wife and my wife is great. There's high semantic similarity between those. They basically mean the same things with some differences. And then low cosine being like, I love my wife and ice cream is cold. Okay, yeah. They're very different semantically. They're not making a judgment call about ice cream. It's a stating a fact about its physical nature. Now, if you go to the next slide, what I have here are 6 sentences, and you can click on any two, and it will highlight the cosine similarity, which is how we measure semantic similarity. That's the best practice for any sort of embedding that you're trying to calculate semantic similarity on. And you can also see the lexical overlap, right? Like the old search term approach of it, like what words overlap in it. And you can see that there are a few key differences, like let's see here, question or sentence 5 and 4, most survey respondents approved the new policy, most survey respondents rejected the new policy. Well, there's a ton of lexical overlap, but cosine similarity, not so much. I believe it's the top ranked lexical sentence pair, but the third ranked cosine similarity pair, right? The meaning is different, lexical overlap. So these are two different concepts. Now, how can we use that? Well, on those 5 different runs, this was for a different study. I was looking at sentiment analysis for something, and I ran each model prompt pair 5 times over 2,210 different calls. And I then embedded the explanations and then calculated cosine similarity between each of the 2,210s within like cosine similarity. So I'm not looking at how similar one question is to another. I'm just looking at how similar the explanations are within a single question. Then I'm averaging that. And the distributions are fairly telling, right? The further right the distribution, so the revised prompt, for example, the red, tells us that those cosine similarities are closer. The explanations have more semantic meaning than their blue counterparts. So the further right this is, the less semantically similar those explanations are. This is just a good representation, in my opinion, of a way we can explore the explanations. And in fact, it also goes to tell us the same thing we were seeing with the direct responses. If you look at GPT-OSS, those distributions are a circle on a circle almost, right? They are just overlapping to the point where they're very indistinguishable, which is not surprising given the direct responses from earlier, right, where we had the agreement rate pretty close. So another way that I thought was interesting to use these was that I used the same sort of within question framing, but I looked at the semantic similarity when the direct response matched versus when the direct response didn't match. I wanted to see like, okay, well, are the explanations going to be the same regardless of the direct response? And what I saw was something that makes me feel a bit better, right? The blue represents when the direct response, right? Like toxicity is true in both these, and then the explanation, the cosine similarity between those explanations. The cosine similarity is higher, meaning that the explanations have closer semantic meaning. Whereas when there's disagreement, toxicity is rated true, toxicity rated false, explanations. We would expect those explanations to be further apart, regardless of the prompt necessarily. And that's exactly what we see across models here. It's just that I haven't fully developed something in terms of models and what that might mean. It is just an interesting way of using these and exploring that shows you that there is connection between the direct response and the explanation. Okay. In the interest of time, when I said I could talk for 3 hours, I unfortunately was not joking. I'm going to give you a quick example on quality criteria and also some further use cases. So LLM as a judge is actually a studied approach to evaluating LLM responses that aren't clearly like accurate or like grounded in some sort of ground truth. And so this is a way of potentially taking quality at scale. And so I took the output of the sentiment analysis that I had done separate from Eric, and I ran judge templates on a small sample of 4. And I asked, and I developed prompts for fluency, coherence, entailment, plausibility. And you can read all those if you want to. And then I looked at the average scores based on a Likert scale. How much do you disagree to, or was it very strongly disagree to very strongly agree, basically. And then what I did was I created a judge, and I role prompted, which is something that, a short aside, I don't actually think role prompting helps all that much. Yeah. But I asked it to be very harsh critic of what's going on. And what it did was it didn't change the nature of its responses, but it did open up a bit more of the distribution in responses. And so that's what, like, this bottom response is the harsh judge. The top response is the non-harsh judge. Similar, but we see harsher responses, which is what I was hoping for. This is just a comparison of the distribution of the direct response across models. And we can see that the not harsh, the semantic similarity is much closer, whereas the harsh model further apart, which is, I think, good. Or I shouldn't say, no, that's not semantic similarity, sorry. That's the response. So it's exactly what I want. I want the harsh response to move to a less friendly territory, because these models are sycophantic. And then this one doesn't tell the full tale, which is part of the point, but I took the harsh responses, and then I wanted to see the distribution of those based on whether they were actually, whether the direct response from the initial sentiment analysis was correct or incorrect. I wanted to see if there was any signal in the noise here. So, like, the harsher it got, was that more likely to be an incorrect response in the model that was initially evaluated? And it doesn't really look like much, except maybe phi4. You see a little bit of a nicer response and a little bit of a harsher response. Except when we actually go and use the various distributional methods to compare the outputs, we see statistically significant differences in the correct and incorrect distributions. Oh no, this is the harsh versus not harsh. What I found was that basically everything but GPT-OSS had statistically different responses. But if you can take, for example, the embeddings and look at the distributions of those and compare them, you can actually start comparing the statistical similarity of explanations also. This is not that, but it is one approach that provides us a way of using this response explanation framework to actually build evaluative evidence. So, okay, if you're still with us, and I appreciate it greatly, three things I want you to note here is that we want to choose statistical evidence when evaluating these things, not just vibes. It's okay to use vibes kind of initially to get your feet on the ground, but when it comes to actually creating reporting standards for rigorous, transparent science, we like going back to our roots in statistics is the way to go. It's important to then collect selection or report selection rationale. And the way we can justify our selections in terms of models and prompts is with these straightforward statistical tests on accuracy or alignment and precision and compliance, right? That's pretty much good enough to justify anything, especially, I mean, frankly, if I saw a paper using LLMs that did any of that, I would just faint out of joy. And then it's also important to note not just the point estimates, but when is this accuracy actually statistically significant versus noise? So what do I want you to take away from this? Well, this is still an ongoing discussion in theory building and the social sciences, for sure. I haven't seen anything articulated like this, nor have I really been able to get reviewers on any of the papers I have out. Not that I haven't gotten it under peer review, it's that the journals have trouble finding reviewers. That's not the point. Uh, the point here is that treating LLMs as measurement instruments give us a way of approaching the way we can actually ground evaluation and justify decisions in research design, right? We're trying to understand not only the data, but we're trying to understand the functioning of the system behind it. I would really argue that if you're using LLMs in any way, like present your findings in terms of compliance, accuracy, and precision, right? These are fundamental, and I will continue to harp on how important these are because I think that you can, like almost any way you use LLMs can do them, right? And that if you present them, hard to argue against. And then finally, you do not have to choose between scale and rigor, right? If you're coding 25,000 articles, you don't have to be like, well, we just kind of hand wave the fact that we use 25,000. You can set uncertainty thresholds, right? You can set benchmarks that you can compare against, and you can do this at scale. I'm not saying it's free. I'm not saying that it's easy. I am saying there is a way to scientifically do this, the way that we can actually not be the unscientific friends of science, of the STEM sciences anymore. We can actually go and approach reproducibility in a very exciting way. So with that, I don't know if there are any additional questions. Feel free to go to my either my blog or my GitHub, and you can look at these slides, interact with them yourself. Feel free to use it. Feel free to reach out to me with any questions you might have. Uh, and with that, I'll turn it back over to you, Eric, for either questions or just, I don't know if everyone needs a 10-minute nap. So
Yeah. No, thank you very much. Really enjoyed learning more about how we can rigorously evaluate these large language models. I think it's a really important and fascinating area of research that you've embarked on. So I know I have a whole bunch of questions, but I have more access to you than most. So let me open it up and see if there's any questions. I did drop a link to the series. So if you're interested in the next session on machine learning and causal inference and high performing computing facility, please feel free to join us. But let me open it up for any questions that you may have.
Right, I'll jump in. I'm Michael again. Thanks for your presentation. Really, really brilliant stuff. I'm wondering how are your colleagues responding in your department? Is this gaining traction? This idea? I mean, I think it's really fundamental to our science. But I'm curious, like, what's the reception that you're finding?
it actually gives people a grounding, which they like. It's not just shoot from the hip, providing direction people respond to. With that said, that's mostly in IIDS, the institute I'm in. We're currently doing a lot of work working on applied uses of AI. But at the end of the day, if you're using an agentic workflow, like where you have many different LLMs calling each other in a chain, you can take these same principles and apply it to the discrete decisions at every level. And so it actually is applying more now than it was when I initially started, because we're finding that if we can evaluate the workflow and find points where, oh, there's a lot of variability in this point, can we improve the prompt? Can we improve something? It doesn't compound errors that tend to lead to problems in enterprise level agentic systems. So with that said, my colleagues in my department don't really know what I'm doing. My colleagues in IIDS do. And the workshops I've led, people like the ability to be able to actually analyze and have some sort of grounding. I have yet to get a lot of pushback from people who understand that what these are. The only pushback I've gotten seems to be from people misunderstanding what fine tuning is versus what just a generated model is. So, yeah.
Have you done any examples of those compounded errors? Yeah, I'm wondering if people just are not aware that, right, as the rush toward agentic happens, that's going to have this compounding effect. And Is that a approach to show colleagues like, hey, if you're using my concern again is people, they're so easy to use, people are
Mhm.
using them and saying, hey, look at these great results.
Mhm.
But under the hood, there's no verifiable traceability.
Yeah.
Um, and that, is it worth saying like, look, here's what happens and here's under the hood. And this is a really bad response. And you don't know that, even though it looks plausible.
Uh-huh.
Right. So,
Yeah. No, you're absolutely right. There is not a ton because right now, um, well, I don't want to say why. I've just seen people who are heavy into the agentic side coming to terms with the idea of compounding errors if they're software engineers. And you have the scientists who are coming to terms with what agentic even means and like trying to use like Claude code. That's me, like I'm over here. What I'm doing personally is using Claude Code to build my personal information system and then wrappers around any sort of agentic system that will log decisions as they go. And so I figured that the more we can make things frictionless in how we do that, the easier it will be. So it's like, hey, point Claude Code at this GitHub to create a wrapper that will help you log everything as you go. That's the future, as I see it.
one other question, more
Yeah.
kind of general social science literature and research. Do you see a lot of uptake in things like consensus and elicit and among your colleagues, again at the department level, those ways to kind of extend your reach of literature and synthesis? What's your sense of that kind of outside your bubble?
I mean, my sense is that people use it more than they say and are definitely using it. Uh, the thing is, like, I'm developing my own like lit review, discovery retrieval, synthesis methods
Lower
because
your own stack.
yeah, I mean, because Claude Code enables that kind of customizability, right? Like, and with our institutional access, getting API access to the journals that your library has is actually not that hard. So you can go download OCR, create just text, have Claude Code, try synthesizing in repeated ways. With that said, like, Claude Code already has like a deep research, just like Gemini and Deep Research Max. But that's not scientific. That's I'm just trying to learn kind of off the hip about this subject. So, like we can learn things from qualitative researchers don't even know how useful they're about to be if they like how much they apply to this because I took the idea of saturation to help me understand concepts and build like sort of gatekeeping metrics on like something I'm doing. It's like I want to understand this topic. Help me define it. So then it's going and pulling articles until it reaches a saturation point with its definition, and then I have a traceability chain. And here's the article we pulled from. Here's our rationale that I can then go back and verify that's what it actually is saying or that's not what it said. So do I see an uptake? Yes, I don't think people are going to tell me. But I think that there's a long-term benefit to us developing our own systems and our own protocols, all with visibility and transparency involved in it. Like for me, it's very important that anytime I do that, I can trace the logic back and I can verify it at any point. I'm not going to submit something if I haven't gone and seen the exact quote that the AI is pulling from to make its point. So, yeah.
Great. Yeah, thanks.
No.
I do get the sense you're in the 0.001% as opposed to the where kind of people are at
It,
overall. So,
and there will be issues with the way I'm approaching it long term, but there will also be people who adopt from this. And I don't necessarily think what I'm doing is all that difficult. The difference is I've just spent the last like 2 months at home with like the curtains drawn, like in Claude Code, trying to see what it does. My failures are greater than my successes. So yeah.
much appreciate your presenting this.
Oh,
So
no
top
problem.
notch.
Great questions. I really appreciate your openness to this too. It's not every day I get colleagues that aren't like about to burn me at the stake. So
Great. Well, I'm seeing we are at the 1:30 hour, or well, sorry, is it 1:30 there? We're all in different places. Michael is
10:30 for me, but
10:30. Yeah.